Yesterday, we spoke about the mathematical concept of infinity, a fan favorite that everyone is familiar with. And we made the argument that infinity is not a concept limited to math class. Infinity is real, and it's something we encounter in our day-to-day life. And the main way we interface with infinity as a concept is through our emotions, our feelings. Using feelings to verify things may be a tad unscientific for some people's tastes, but I don't think it's a stretch to accept this as true. I would even say that it's obvious. So I want to make an argument here. If we are willing to accept that infinity is real and we encounter it, then it would be valuable to learn more about it. But what is there to learn? It seems by nature an impenetrable concept. Infinity. It's so big that we don't understand it and we move on. But mathematicians have discovered a lot about the concept of infinity. And in order to understand our concept of the day, we have to make some quick distinctions between types of numbers. The standard whole numbers we are familiar with, 1, 2, 3, 4, etc., are known as the natural numbers. And there are an infinite number of them. This should pass the sniff test. Makes sense, right? You can just keep making them bigger. But now let's add some more numbers in there. So we'll keep 1, 2, 3, 4 going up. Let's also include decimals and fractions like 1.5 and 9 over 10. And let's throw some funky numbers in there too, ones that we really can't represent as fractions or decimals, like pi or square root of 2. So we combine all those types of numbers together, and we get a set of numbers known as the real numbers. There are also an infinite number of real numbers, which should again pass the sniff test. Makes sense. Like we just added more numbers to an already infinite amount. So there are an infinite amount of natural numbers and an infinite amount of real numbers. But you may be surprised to learn that there are more real numbers than there are natural numbers. They are both infinite, but one is bigger than the other, implying that there are infinities of different sizes. This was illuminated in 1891 by German-Russian mathematician Georg Cantor and his famous diagonalization arguments. So how do we know that one infinity is bigger than another? Or in other words, how do we know if two groups of objects have the same amount of items in them? So let's imagine that I had a container of cheese slices and a sleeve of crackers. And let's also imagine that every time I took out a cracker, I put a piece of cheese on it, creating a lovely snack. Eventually, I would get to the last cracker in the sleeve. And if my very last cracker corresponded to my very last piece of cheese, then I could conclude that I had an equal number of crackers and cheese slices. To put it another way, there was a one-to-one mapping of crackers to cheese. What Cantor proved was that you could not map the natural numbers, our familiar counting numbers, to the real numbers. There would always be more crackers than there were cheese slices. And if you kept on eating, your mouth would get pretty dry. Cantor's proof was revolutionary in every sense of the word. I would recommend anyone who is curious to look into the details of the proof. It was a new style of proving things that ended up being very useful for pushing mathematics forward. And it wasn't just the style, it was the implications. Cantor's discovery was opposed when it was released, and the merciless public persecution he received led him to serious bouts of depression for the last 4 decades of his life. Cantor was a devout Christian, and other members of the church saw this idea of multiple infinities as heresy. They believed that Cantor was trying to provide evidence that there were multiple gods, and saw his work as a challenge to the absolute infinite nature of the Christian God. And the math world was not kind to him either. The other mathematicians of his age decried him as a charlatan and a corrupter of the youth. It's not all gray skies for Cantor, however. He did eventually receive the highest medal of achievement for mathematics, and the leading mathematicians of the 1900s, the next generation, were all huge fans of his work. So, what are the implications of there being different magnitudes of infinity? We will pick up on that discussion on Friday. Tomorrow, before that, we will be exploring some of the other curious properties of infinity that mathematicians have discovered. And that's all for today's video.